Hello there. Today we're going to look at On the Measure of Intelligence by François Chollet of Google. This is a bit of a special episode, I would say, because if you look at the paper, it is, first of all, it's very long, and then second of all, it is a wall of text, basically. Now, it's very interesting text, but if I were to go through this with you, we'd basically just be kind of scrolling and reading along. So what I've done is I've basically read this and taken notes, and I will attempt to just tell you what happens, at least for the first part. So I intend for this to be a multi-part series because it's so long. So the first part, as you can see here, is context and history, which is a little less boring than it sounds. The second part is going to be a new perspective where Chollet proposes his measure of intelligence. And the third part is going to be about the benchmark, the ARC benchmark that is currently, I believe, running on Kaggle. So as it looks right now, 3 parts, and today we're going to dive into that first part. So here we go. He basically says that we need to define what intelligence means. We need an explicit goal to measure where, if we think about AI, like artificial intelligence, what does intelligence mean? We need something where we can basically put a number or multiple numbers on it and says that's intelligent, that's not intelligent. What we have right now is just basically anecdotes. It's just we all kind of feel what seems intelligent, but we are not like sure. And sometimes it's very misleading. He brings up the Turing test, for example, which is that you have a computer or a human behind a wall, and on the other end sits a human, and the human needs to kind of communicate without seeing what he or she communicates with, and then determine whether or not on the other side of the wall is a human or a computer. And if the computer could fool a human into kind of a 50-50 guess, then the computer would be passing the Turing test and therefore intelligent. Now, Chollet doesn't go right now into why that's not sufficient, but he's basically saying this is not sufficient, it's distracting. And second of all, it's basically just outsourcing the problems of defining intelligence to human, right? To this human right here, who is fallible and noisy, and doesn't really know. All you tell the human is basically like, is this thing intelligent? Does this thing seem human to you? It's also not clearly defined. So we need something more, and Chollet says the definitions that exist today of intelligence are basically they are implicit definitions that are loaded with biases, and biases basically from a human perspective on what intelligence is. And if we want to really make progress in terms of measuring intelligence, we need to point out these biases that are in these measures. Okay. It has a range of quotes, namely one here. Intelligence measures an agent's ability to achieve goals in a wide range of environments. That was, I believe, the conclusion of an author that distilled lots of different definitions and tried to distill them into one sentence, and that's it. Intelligence measures an agent's ability to achieve goals in a wide range of environments. So the crucial part here is to ability to achieve goals. So the agent must be, doing something useful, doing, like in reinforcement learning, we'd say it must be getting higher rewards. And the second part is in a wide range of environments. So the notion right here that we're going to encounter time and time again is basically an addition of skill and adaptivity. So it's not enough to have high skill. You also need to be kind of adaptive to very, very different environments, to a range of environments. And that's this is the main issue that Chollet has with the current sort of definitions of intelligence and the current direction of the AI field, because it mostly measures skill and not generalization or adaptivity. Now, he says in this thing, in this sentence right here that you just saw, there is an implicit sort of something is said implicitly, namely that these skills, this ability to achieve goals in this wide range of environments, it must be acquired, it must be learned. These new tasks, these different environments, the agent should basically learn to adapt to the different environments. Then the agent is intelligent. It's not that intelligent when it is sort of pre-programmed to already handle these environments. So he says that's sort of implicit in that statement, and we're going to see how this is made explicit later. He goes into basically there are two different viewpoints on intelligence, this old nature versus nurture debate, and that refers to two things like crystallized intelligence versus skill acquisition intelligence. So the evolutionary view would be that intelligence is sort of this set of static programs. And here we simply kind of boil down these two views to their extremes, right? So I don't think any major evolutionary biologist is that extreme right now. But these were historical set of views that were held. One of them was that intelligence is basically just it's all pre-programmed into you by evolution. So you can solve this puzzle because during evolution, your ancestors that could solve these puzzles were survived. You can plan your path through a tree jungle because that was beneficiary to you, and so evolution put that into your brain. And therefore, what results is AI is the science of making machines capable of performing tasks that would require intelligence if done by humans. That's basically what Minsky said. It's a quote, I believe, by Minsky. At least Chollet says it's by Minsky, or I misread. Where if you have this set of view that AI is basically just this set of static programs, that means that if a human applies that set of programs to a task, right, and the human achieves 200 points, it means if an AI comes along and achieves 201 points, then it is intelligent because it has simply the better set of it has outperformed this static set of programs. Intelligence is this static set of programs, and the AI has a better set of programs. So it's basically, Minsky says, if we know of a task that would require intelligence if done by a human, then something that can solve that task is intelligent. And this equates learning basically just to memorization. If you ask a proponent of this viewpoint, well, what's learning? Like, if everything's pre-programmed, why we can still learn? And they would say, yeah, but the learning is just you memorize situations, and that particular ability is also pre-programmed into you. The other extreme viewpoint is this tabula rasa viewpoint, where it basically says you come into this world and your brain is a blank slate, and all of your abilities you basically must acquire through learning throughout your life. So this is another extreme viewpoint. And in terms of intelligence, where that leads is following. AI is the science and engineering of making machines do tasks they have never seen and have not been prepared for beforehand. And that's a quote by McCarthy. And Friedberg, if we're ever to make a machine that will speak, understand, translate human languages, solve mathematical problems with imagination, practice a profession, or direct an organization, either we must reduce these activities to a science so exact that we can tell a machine precisely how to go about doing them, or we must develop a machine that can do things without being told precisely how. So this leads to more of these notions right here that you can see here, the machines have not been prepared for a particular situation. So if we make a machine that can do a task that it has not been prepared for, we we know it's basically intelligent. And again, so if we make a machine that can do all of these things, all of the things right here, then either, Friedberg says, we must reduce these activities to assign. So basically we must program the solution in there already, or we must develop a machine that can do things without being told precisely how. And as you might realize, this is much closer to the machine learning paradigm. It's all about how much you say precisely, because the extreme proponent of this thing would basically recognize any sort of learning, anything that you haven't seen before is intelligent, right? If you can handle any new situation, you're intelligent. And Chollet is going to argue that that's also not really the case. Like, we have to be a bit more graded about it. But this is basically the machine learning approach. It's we build machines that can do things without being told precisely how, that they have not been prepared for beforehand. Like, it can solve things that are not in the training data. That's one interpretation. And if you're a very strong proponent of this, you would call that intelligent. And Chollet is going to argue that the truth, of course, is somewhere in the middle between these two viewpoints, and therefore defining intelligence in either of these terms is going to lack in expressivity and in usefulness. So, how do we evaluate AI? And Chollet goes through different levels here of AI evaluation. So, first of all, he contrasts these two things right here: skill-based evaluation and generalization-based evaluation. So in skill-based evaluation, you basically go for one given task. So you evaluate a system on one given task. One example here is, for example, the Turing test. And that's done by human review. Another example is where you have like a proof. So you evaluate a system by giving its optimality proof. You can analyze it and you can say it is always correct at this particular task. What you can also do is this peer competition. So this is maybe what we see in sort of like chess. So we let the bots play first humans, and then we let them play other bots, and we determine which one's the best. And also the most familiar one, benchmarks. So this would be where your ImageNet test set is, right? That's right here. That's a skill-based evaluation. That's one given task. How well can you solve the ImageNet test set without looking at it? That's one task. So the problem, Chollet says, with this skill-based evaluation is sort of obvious. It's like a single focus. You can't, you are only good at this particular thing. And that is one of the examples of this is the fact that the Kaggle models are usually, the winning Kaggle models are usually useless outside of that particular data set, because they're just so hyper optimized and hyper focused on winning that particular Kaggle competition. So it's actually a pretty strong science on how to set up a Kaggle competition such that you can then use the model, the winning model afterwards, for doing something actually useful. There are no conditions on how to arrive at a solution. And there Chollet lets a bit of that's basically his point that's going to come into the measurement later, into the math, where he says you simply have to arrive at a solution in this skill-based evaluation. This skill-based evaluation usually doesn't care how you arrive there. So the ImageNet test set score doesn't care how you got the neural network or whatnot that you got. It simply cares how many images do you classify correctly. And this leads to what is called the AI effect, which I didn't know it was called like this until recently, but it's fairly obvious, where people come up with a task that is intelligent. So people used to say, oh, checkers. The game of checkers It requires intelligence. And then you build a machine to solve checkers because you can just, I don't know, search, do like a bit of a smart tree search, and you solve it, and you tell them, here's like a tree search that does checkers, and they'll say, well, but that's not really intelligent. It's just like a tree search. But chess, you can't possibly do the full tree search. So chess is intelligent. And then you build like a smarter tree search, like you build stockfish, and they'll be like, yeah, but that's just, that's just this machine thing. And so the goalposts keep moving. Every time they come up with a task and you solve the tasks, they'll just say, that's not really intelligence. This next task, that's intelligence. And it's easy to see that if you just do this skill-based evaluation, you will never get there, because it's always going to be, the next task, the next task, the next task. It's overly anthropocentric. It's overly based on how humans view the world. And what is not left in here, and again, this acquisition, what is not in this definition is the fact that why do we think that someone that plays chess very well, like why do we think Magnus Carlsen is smart? Why do we think someone like a Go master is very intelligent? And that's because we know that this person is human. At least we believe. There are doubts about some of these grandmasters, but we believe that they are humans, and therefore we know that they have only had 20, 30 years to learn this, and they must eat regularly, and they can only think so fast, and it's hard to memorize things as a human. So we know all of their constraints that went into learning this, and we basically know it's not like we are not aware of something like Neo has in the Matrix, where you can just upload the solution to chess into your brain. We know what's required to achieve that level of success, and we know the only way this can be done is through general intelligence. We know that there is this correlation in humans that if you are good at chess, you must have this, or you're very, very likely to have this general problem-solving ability, right? That's a human-centric view, and that does not count for machines. Machines can take forever to calculate. They can distill years and years of experience, like thousands of years. And this would be the same case with this OpenAI Dota 5, right? Dota 5 is exactly here. AlphaGo is exactly here. We only think they might be intelligent if a human does it, because we know what's required for humans to get there. Again, focus, skill acquisition. Now, you might be bored a little bit. Okay, it's about skill acquisition. But think about it. It's not that easy to actually define this skill acquisition thing without falling back into the exact same trap. So it goes into say, okay, as opposed to this skill-based, we can measure generalization. So what's generalization? Generalization is the broad ability to handle tasks that differ from previous tasks. So you have a task and it's different from previous tasks, you generalize. Now there are two ways you can view this. There is system-centric generalization, and that's basically if you take the strict definition here. So this would be a machine learning system trains on the training set and then is evaluated on the test set. It has never seen the test set before, so it's generalizing, right? That's called system-centric generalization. But that's not really enough here, because we also need to take into account the developer of the system. So developer-aware generalization means that you generalize to situations that are new to the system and to the developer. So a developer of an ImageNet model knows that it is going to be evaluated on the ImageNet test set. And that is in this category, system-centric, because the developer knows. However, a broader generalization, this developer-aware generalization, also takes into account that fact. And it would say developer-aware generalization is only when the system generalizes to something that is not known to developer, that is new to even to the developer themselves. They haven't foreseen that. So this accounts for prior knowledge of the developer. Chollet defines different degrees of generalization, largely along these lines. So absence of generalization is when you have like an algorithm that you absolutely have built in that it works for every possible situation, like a sorting algorithm that you have mathematically proven to work for all sequences of numbers. No generalization. Everything has been foreseen. Then there is local generalization, and this in machine learning we call this something like robustness. This would be your test set robustness, your small distribution shift. So the test set here comes from a known distribution. So this is the notion of known unknowns. You have an idea of what can come at your system, and you require a dense sampling of the input space. Usually machine learning training sets are very, very densely sampled. That means there's a lot of data there that we can learn from. So we have like lots and lots and lots and lots and lots of data. And when the test point comes, it is going to be like somewhere really in between all of these training data points. So we can infer from the surrounding training data points what the test data point is going to be. Like if there's a classification boundary right here, we can sort of nearest neighbor it. And there are arguments that deep networks are basically large nearest neighbor classifiers, but that's a topic for another day. And we are here basically. We are here in machine learning right now. We do local generalization. We know our unknowns. We know our test set. As the opposition to this is broad generalization. Broad generalization is where you don't know what you don't know. Unknown unknowns. You don't know what comes at test time. And you can't pre-build sort of your expectations into the system. This is more akin to something like level 5 autonomous driving, where you build this car, but you don't really know what kind of situation's coming. No, this is a fuzzy definition, right? I mean, you do sort of know what situations will come at the car. You can certainly probabilistically make a statement about what. So it's not a clear-cut definition, and I think we're going to. So in the math, it seems clear-cut, but when we get there, I don't think it is that clear-cut, honestly. It's still kind of an intuition thing, what you categorize as local and broad and so on. Also here, the Wozniak coffee cup example, where basically Wozniak says you should be able to build a robot that goes into any kitchen and gets you a cup of coffee. And here you have unknown unknowns, because you can't possibly foresee all possible kitchen arrangements. There might be obstacles and so on. There might be different coffee makers that you've never encountered before. But I've long been saying that this is a bit of a trick right here, because what you can always do is you can construct a kitchen, right? And right here is the coffee machine. So there's how do we draw this? There's the coffee machine right here, one of these fancy Nespresso machines. You put in a capsule here. And here's the coffee machine, okay? But then you build a wall around it, and the wall has a door. And the door will only open if you solve an IQ test, right? So or any sort of test. So whatever you put in that spot, that's the level of generalization you can achieve, basically. So you can always up the level of generalization to or you can put, I don't know, you can put the halting problem here, right? You can say you only solve this door if you can give me a proof of the ABC conjecture, something like this. So coffee cup example kind of has some backdoors. In any case, you sort of know what Wozniak means. You should be able to go into a standard kitchen, but the standard kitchens are still diverse enough you can't foresee all of them. I don't, if any of you has this sort of kitchen that I'm talking about, like, mad respect. We'll all get this robot, and you'll just have to wait for the next iteration. Okay, then there's extreme. Extreme generalization is where you have kind of open-ended. You don't know what's going to come. You don't even know the broad category of task that is going to come, right? Broad still refers to a broad category of related tasks. So it is sort of a general ability. And the extreme generalization just means, whatever comes, you can solve it. But it is different from universal. Universal generalization, Chollet says, is any conceivable task in the universe. And that's pointless. It's pointless because it's just too much. There's this no free lunch theorem, right? Plus, what we actually want is we want human level intelligence. And human level intelligence has this property of extreme generalization. With extreme generalization, we mean the scope. See, it's dependent on a scope. We mean the scope of all human tasks, of all tasks that humans could produce or could find useful, could find themselves in, or could pose of this system. Not all tasks that the universe could pose. So that here you don't even have the relation between tasks. The relation between tasks are at most abstract. So maybe it's like the general ability of sorting things generally in whatever fashion, and things, whatever these things are, with whatever properties, or the general ability to communicate an idea or something like this. And this in humans is called the G factor, or it's related to. But we're going to take Chollet really goes after psychometrics here and really models his framework after psychometrics for humans. And the sort of achievement in psychometrics, one of the achievements is this measure of the G factor. And that's what we humans usually call intelligence. He says, note that humans have system-centric and developer-aware generalization, though, that one, this contains the other one, so why? Because we can handle situations that previous humans haven't experienced. Now, I'm not sure. He basically says humans have developer-aware generalization because we can fare well in situations that no humans during evolution have experienced prior. But okay, let's have this abstractly. Let's say our developer is the evolution process. You still have to ask, can humans really solve things that the evolutionary process has not built into them in some sort? I guess that refers back to the nature versus nurture. Like humans cannot, multiply long floating point numbers. It doesn't matter how, I guess without a pen and paper, it doesn't matter how much you learn or something like this. There are some things that they just can't do but would want to do. And I guess the evolutionary path simply didn't provide us for doing that kind of stuff. We have a finite working memory and so on. So I think the discussion here is still to be had if we really do have developer-aware generalization, if you consider our developer to be the evolutionary process. But we can forgive a little bit here. So this is the general diagram that also emerges from kind of theories of intelligence from psychology, where generally you have a general intelligence factor, which is one factor. This is quite remarkable in humans. There is one general intelligence factor statistically. All these general intelligence tasks, they broadly correlate, and lead to one statistical factor. It's not obvious why that should be, but it turns out to be one factor that distributes hierarchically into these things, which are called broad abilities, broad cognitive abilities. And in Chollet's framework, that would correspond to broad generalization. And then these are again hierarchically subdivided and sometimes, as you can see here, shared task-specific skills. Okay, and this in Chollet's framework would be local or no generalization. So again, he basically goes into psychometrics and specifically IQ tests for humans. Can they inform the measuring process? The thing to note here, according to Chollet, is in an IQ test, you want to measure these broad abilities. You want to measure, ultimately you want to measure G, but even if you measure different things in psychometrics, you want to measure these broad abilities. But these are abstract concepts. So what you're left with, what you can only do, is you can only measure really tasks. Okay, and is this wrongly numbered or is this intentional? I don't know. You can only measure tasks, but you somehow have to make an inference about the broad ability from measuring the tasks. So that's the difficulty in psychometrics, right? You want to measure the abilities, but you can only measure tasks. The abilities are abstract concepts, and the skill are the measurable things where you can put a number on it. Now, you can. So what these IQ tests do, they usually employ these broad battery of tests. So you don't give the human just one tasks, you give the human a lot of tasks. You're like, okay, complete this series. Which number comes next? Rotate this in your head, and so on. But they're also very human-centric things like reading comprehension and so on. But you do this broad battery of tests, and you might think, okay, this is sort of like the Atari, suite, where one reinforcement learning agent has to solve these whole bunch of Atari games, or a superglue in NLP, where one NLP system has to learn to do all these different NLP tasks. There is entailment, there is sentiment, there is Boolean question answering, and but this is, according to Chollet, it's sort of not really, it's not really the case that these are equivalent, because it is a battery, but it is known to the developer. So the developer knows that the NLP system has to solve the superglue thing. So the developer can, first of all, train the system until it reaches a good superglue score, but then also it will have built in already the assumptions of the developer that you have to solve this. So the second important thing about these battery of tests in IQ test is that they are unknown to the tested. The tested cannot, or ideally should not, practice for them. That's why people keep developing new and new IQ tests, because we sort of know they all correlate, first of all, so they measure the same thing, but also second, because otherwise people, if you just always do the same test, people could practice it, and then you would no longer measure the general ability. You would only measure that one test. By the way, that's also why a lot of these, brain exercise apps and so on, none of them really ups your intelligence. You only get better at one app if you do that. You don't get smarter in general. So and Chollet says there have been a number of attempts at making AI solve human IQ tests, right? Well, the reasoning is the follows, like, humans develop IQ tests for humans, and presumably those are not known, and so on. But again, the tasks broadly of IQ tests are known. I guess really IQ tests work on humans because they only work on humans who don't really care. Like if someone really, 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 really cared, they would, research what kind of tests there are. They would look at all the tests from history. There's only so many tests you can come up with. The new ones are going to be like variations on the old ones. So you could technically, if you really wanted, you could like prepare super hard, and that's exactly what developers are going to do. They're basically going to look at all these tasks, they're going to pre-solve the problem, and then they're going to program their pre-solved solution into an AI system. So we can't just let AI systems solve human IQ tests. What we need are tests that are reliable, which means they're reproducible, that are valid, that means they really measure IQ, or they really measure artificial intelligence and not just task specific skill or something else. They're standardized across the spectrum, so they're standardized so everyone can do them in the same way. By the way, the current benchmarks are standardized. That's the good part about them. And they should be free from bias, which means they should not measure anything orthogonal to what they claim to measure. And the example he gives is they should not measure reaction time, which is also a big component in human IQ tests. You also measure how fast the human is at the test, and the machine, obviously, if you simply put more electrons through the cable, it's going to run faster. Or if you put more GPUs there. So in broad terms, what we should focus on is this new skill acquisition, as I said from the beginning, but it is not as easy as you might think right now. And we're going to dive into the next episode, and it's going to be math heavy. And that's going to be fun. So I hope you enjoyed this kind of special episode. Maybe let me know if you like this style. The paper doesn't have any pictures, so you're just left with what I'm drawing. If you enjoyed this, leave a like, leave a comment, share it out, and I'll see you next time. Bye-bye.